All right, here in this new lecture of Verilog series, lecture number 8, if I'm not wrong, we are going to design a 4-bit adder, uh, 4-bit full adder. So, let us see how we can achieve this. For this, one second. For this, we need to have inputs of 4-bit. So, 30, we assign an array. Let us say A, we have first. Then we write, let me align this in this side for now. And we have input, uh, sorry, 320. Here we have a B, and then input we have a carry in, and then for output, we have uh, three of the sum variable, and we have output carry also. That output, see out. We name them our variables as this. Now, there are many ways to design a 4-bit adder. One we can use is import any full adder module, imply the single bits, and proceed in the same way. But there is another way which we are going to discuss. This one is much nicer and easier. We will just use what we say data flow headed modeling. So we will just do what assign. We will just assign this C out and sum as a plus B plus C. This one is more easier in compared to the importing of full adder module. So let us just try to save this one. And here we have once it is saved, we will just open elaborated design. Hmm, till then, let us see if it works. One second. Um, so here we have it will just sum A and B first, then we'll sum the C in and A. It's stored. We have now 5 bits output, and it will store a 3-bit to inside the sum, and sorry, 4-bit inside the sum, and one last bit MSB inside this C out. So this was the case of. So this is how our schematic works. You can check my GitHub also. I have uploaded lot of projects there. I have uploaded Ripple Carry Adder. Look ahead Carry Adder. I will add multiple advanced projects there. Vedic Multiplier and Koge Stone Adder. These are must quite efficient adders. So those projects you can add in your resume also. So now we will design a simulation file. Let's name it as test bench, and inside this test bench we will just verify whether our outputs are coming or not. So this time I'm not going to use the loops because loops are going to take a lot of time. Since there are 4 bits, so there could be a lot of combinations. Okay, 2 to the power and combinations. So that those much combinations I'm not going to discuss here. So go to the source, go to the simulation in the SIM, click on the test bench, hide our panel, maximize it. Uh, so let me move this time space here. This we will assign our ports here. The type for 30 A comma B. Regitype for C in, wires for 30, sum, and a wire for C out. Now we will instantiate our module that are created bit underscore for adder. This should be underscore. bit underscore forwarder design under test. Now we will just instantiate connect the ports dot A to A dot B to B. Dot A means 4-bit address port to the this inside is the this test bench port which we are assigning here. Dot C in to C in. Why I'm naming them same? You can name them different also. But I am naming them same because sometimes it create complexity or confusion that which has to write on the left and which has to write on the right side. So here we will write dot sum to sum uh, dot C out to C out. Now our work mostly our work is done. Now we need to just create the initial block and assign the values. Initial begin end it should be begin and inside this block let us just call for display here display 4-bit adder uh, will say here monitor so the monitor will display let us call the tab here so it will display a equal to percentage b tab here b equal to percentage b and c tab is c uh, c equals to percentage b and this let us separate them uh, sum equals to percentage b let me add some spaces between them so it could be comprehensible much here we have just add tab here and last one is c out okay carry out and let us write as percentage b assigning them now let me write all of them in the order a b and C in, it is not C, it should be C in. Let me write here. More comprehensive it will be. So, and here we have sum, and then lastly we have a carry out. Now, just assign the values. Let's say after some delay, we have A equals to 4 bit, no, 4B 1011, B equals to, for now, let's say 4B 0001, and let us say C equals to 0. C in equals to 0 and after let's try this 10 commands here it is to say it is causing A and B are okay these are the capital letters okay these mistakes happen sometimes okay now that there is no error let me replicate them for the fourth time let us say this time I will set the scene as 1 now this time let us take 1000 and with this time I will take it as B1111. Let's see in a 0 and let me copy this line and paste over it. And this time I will set C in as 1 and then I will just say finish. So our test bench is created. I hope there is no error. We made it successfully till now. Now we only need to do is simulate our test bench and check our program whether it is giving the correct output or not. In the next session, either we will start the force half subtractor or we will move towards the ripple carry. So initially there was nothing. So sorry, it is. I guess I assigned some wrong. Yeah, okay. Here it is and B. and B, any problem else? C out, blah blah blah. So this shouldn't be like this. Let me check once again. A is percentage B is percentage B, C is percentage B, sum is percentage B, C out is percentage B. Okay. A, B, C in sum, C out. Assign C out, comma sum, A, B, C in. Okay. Let us save it once again. So remove this file, or we don't need this file. Let us run the simulation once again. Now let us see what are our outputs. So here we have C in is 0. This will become, once we will add 1 here, this will become 0, it will become 0, it will 1. So 1, 1, 0, okay. Now we will do the same case with just C in as 1, so just add 1 here. So this is showing the correct output. Now let's go ahead to the simulation schematic. We click on the full. Now just go to the radix. We will convert it to unsigned decimal so we can clearly understand what is there. So 11 plus 1 is CC, is that 12. We will move to the unsigned decimal. So here we have a 12. So till here it is 12 because the C in, let me change the color of the scene, signal color, magenta. So till here scene was 0, so we got 12. Now till here scene is 1, so we got 13. Here we have a F, so that is 15. So let us convert it into the signed. So here we have 8, 15. So we got 7 and 8 as a carry. This will explain much more in the case of binary, that how it is working. Let us move to the TCL console and see how it is happening there. So here we have 15. So if we will add it, there will be, since C in is 1, so let us say we add this in here. So 1, 1, 1, 1, so it all will become 0 and C out as 1. Okay. And then we will add this, we will get 1000 here. Sorry, we will get 0, this is 0, 2, 4, and we will get 8 here and C out as 1. Okay. Carry out here as 1. In case we have a C out here as a 1 and here also C out as 1. C out what? Here also we have C out as one case of C in 0 and C in 1. Okay, that's it. Here we got this, and here we got. Let us see once again. I made some mistake. What? Okay, okay, that is fine. We add this. Okay, that's fine. So, so we created a 4-bit adder. You can create now any bit adder uh, using this technology. So I was telling about module association. Let us say we have any module, say full adder, and we name F0 first one. We can just name them. Now we design in the previous lectures. We have seen that often we designed a full adder with inputs A, B, C in, sum, and C out. Now, this will be your assignment. You can check on ChatGPT also that how you can create a 4-bit adder using the instantiation of a full adder. How using a single full adder, how can create a 4-bit full adder. So yes, need to do is you need to replicate this is 4 times. We will create some wires for the carry. Let us say initially we have an array. So A0, B0, we are just connecting in the same order, that is port to input is firstly it is C in, and assigning has a sum 0, and now let us say the next carry will be, so for that next carry we are assigning this wire C1 and C2. We will assign them C1. I am telling how we are going to proceed. Okay, so let us copy this line. uh, Sum 0, sum 1, sum 2, and sum 3. So here we will just replace F1, F2, and F3, and A1, A2. A3, B1, B2, B3, and now here will be C1 because this input carry output carry will not be now our input carry here. So now here let us write C2. C2 will be here. The last one will be C out, so that is not our problem. We need another one, so we will add just extra C3 here wire, and here we will replace it by C3, and our C3 output will be our now input carry here. Now we will assign some one here, some 2 here, and some 3 here. So finally we created a full adder. You using any problem here? A and B are not declared. Oh, now let me make them small letter. That has become a nerve only. So this is fine. Okay. Now for understanding, let me create a full adder for you so that we can see what will be output. Full underscore adder. Okay. Uh, Finish it. So in the sources we have a full underscore adder. Let me design it for you quickly. Uh, so we have a input ports, input A, uh, input B, input C in, output sum, and output C out. Now, in the same way that we did, what we will do is we will assign C out comma sum equal to A plus B plus C in. So we did it, just need to save it here. We named as full adder. Let us remove this schematic discard here. Now we created a full adder. Now let us remove the test image now. It will give the same output that we see. So we created a 4-bit adder, full adder x1, x0. So we assign the ports corresponding to the input values. We name it now. Let us try to full adder, I think, make it IP hierarchy. Okay, leave it. Open the schematic here. Reload. Let me reload the schematic. Now you will see how we are creating full adder this time through schematic. So we are using the multiple full adders to create a 4-bit full adder. It did not reload. It means it is not understanding this file. It is 1 second. I need to make this module on the top. Uh, Move to the simulation sources. Hierarchy update. There was something I am missing here. I need to just a second. 4-bit address. I did not save this file. Okay, okay. Now it is reloading. Okay, what happened? 1 second. Let it get reloaded. What happened? Did it create or not? 1 second. Let me do it. Here it is. So as I said, using multiple full adders for the inputs bit F0, then it is transferring to the F1, then it is transferring to the F2, and you can see the C out here is acting here as an input C in. Here C out is acting as a C in for the third one. Here we have a carry out that is acting as a carry in for F2. So that I told you. Let us see one that is output carry for the addition of some of first bits will act as a input carry for the addition of second bits. So that's how we created a hierarchical form of a full 4-bit adder. So I hope you understand we created 4-bit adder in two ways. First was simply assigning them, and second was creating a full adder module uh, separately and using that full adder module to apply on the individual bits. Now it will be your work to create a 8-bit adder or 16 or 32-bit adder. If you want to see, I have created a 32-bit adder. You can check it on the GitHub repository. It will be on the top of the repository. I've created multiple folders there, so you can check them there. Okay, so that's it. Thank you.